In 5.2, we are now going to transition away from all polygons and move directly into our first four-sided shape. Our first four-sided shape that we're going to deal with is something called a parallelogram. You've learned them before. If you see this shape, when you read it, I want you to remember that that means parallelogram. A parallelogram is a quadrilateral which is defined as a four-sided shape with both pairs of opposite sides parallel. That's its definition. It has to have four sides and both opposite sides, this side and this side, has to be parallel. If I were to be drawing something for that definition, it would look something like this. If I know that these two are parallel to each other and these two are parallel to each other, then I know it's a parallelogram. And so, if I know what a parallelogram is, there are certain properties that each parallelogram has. If I know it's a parallelogram, these four theorems state that these properties are true. First and foremost, if it's a parallelogram, the opposite sides are congruent. That means that this side will be the same length as this side, and the top will be the same as the bottom. If you know it's a parallelogram, then this is true. If it's a parallelogram, then the consecutive angles are supplementary. So what that looks like is this. Angle 1 plus angle 2 adds to 180. Let me zoom in on that because I know that's a little bit hard to see. If I had angle 1 and angle 2, these two add up to 180 and these two add up to 180. These are called consecutive angles. They are supplementary in a parallelogram. In a parallelogram, if it's a parallelogram, the opposite angles are congruent, which means that this angle here has to be congruent to its opposite angle. That the other angles are also going to be congruent to each other as well. Otherwise, it would not be a parallelogram. And lastly, the diagonals bisect each other, meaning that this diagonal cuts the other one into two equal pieces, and same with this diagonal and the other diagonal. It makes this thing that looks like these two are the same and these two things are the same. So every single question besides the proof is going to deal with some of these facts, some of these properties. And even the proof is going to have some of these properties in them as well. So I have some examples for us to do. I've chosen number 3, number 4, and number 6 for us to do. Number 3, the reason why I chose it is because it's a proof. And I know that some of you still have some issues with proofs, and they do not go away. They will be on almost everything all the way through the end of the semester. So we might as well get used to it, and you're getting better at them, I'll be honest with you. There are some people whose tests I was grading, and I saw the proofs, and I was like, oh, they really understand this part or this part. They don't really know what that means yet. I could tell what you understood and what you didn't understand by how the majority of you were filling in your proofs. So let's talk about each of these things and let's go for it. First and foremost, what's given? This is a parallelogram. We need to prove that this diagonal bisects that diagonal. How are we going to do it? It's going to have something to do with something we did in chapter 3 with angle side angle. Okay, so let's go in and go through it. ABCD is a parallelogram. That's given. Why do I know that AB is parallel to DC? Why do I know that these two things are going to be parallel to each other? What am I using that we started with? What definition am I using? Of, not or. Well, yes, definition of. And you can write out the word, or you can use a symbol. It's up to you. Because it's a parallelogram, earlier we wrote down It's a quadrilateral with both pairs of opposite sides parallel. We're using its definition to know that this fact is going to be true about it. Then it says angle 1, let me go to angle 1, is going to be congruent to angle 4, and 2, let's use a double, and 3 are going to be congruent as well. We know that these are parallel, and then they go right into the 1 is congruent to 4, and 2 is congruent to 3. There's a name for those angles. Is it coming to your head? Do you know what those type of angles are called? If you know it, say it out loud. Alternate interior angles. There's actually a theorem in our book. I'm going to put theorem right here. That theorem states that if two lines are parallel, and there's a transversal that goes through it, if two lines are parallel, then the alternate interior angles are going to be congruent to each other. But if you wrote alternate interior angles, I'm going to accept it. If you forgot the little theorem part, I would still say, they're close enough. That's just because I'm a nice guy. You're so nice, Mr. Paramo. I know. Number 4. How do we know that AB is going to be congruent to DC? How am I going to know that this length is the congruent to that length? Now this one's different. Somebody said in my other class, can we use the definition of a parallelogram? I said, well, what's the definition? Opposite sides are parallel. Now, we can't use that. What we can use, though, is a property. If I know that a certain property is true, we just say, what does the property state? Opposite sides are congruent. We've already said that it's a parallelogram, so we don't need to say because it's a parallelogram, the opposite sides are congruent in a parallelogram. You could say in a parallelogram if you wanted to, but the opposite sides are congruent. We've already stated that it is a parallelogram. Which now makes this in the picture. AB is congruent to DC. And then it says angle side angle for number 5. And this is one of those postulates that proves two triangles are congruent. So I know I have to have a triangle congruent to another triangle. Which one do we want to use? ABE? If I use ABE, then I'm going to use CDE. They're going to be congruent to each other by angle side angle. And then it's going to say segment AE is congruent to CE. This is going to be congruent to that. And BE is going to be congruent to DE. So let me put a double, double, and a triple, triple. In-N-Out burger. How do I know that these are congruent to each other? Which thing am I going to use? Let's see if you remember. If you remember, say it out loud.
Corresponding parts of congruent triangles.
Okay. You could write out the whole thing if you wanted to. You could write out corresponding parts of congruent triangles are congruent. Or you can just abbreviate that to Cpctc. Now what we are trying to prove is that this bisects that. And now we know that these two things have been cut into two equal pieces, and these two things have been cut into two equal pieces. We know its definition of a bisector. All we have to do is fill in AC and BD bisect each other at E. Proofs you use either theorems, definition, postulates to fill them in. They're not that bad. Next example, number 4. I chose number 4 on purpose because I know some of you will need a reminder. Find the values of x and y in parallelogram PQRS. So PT is 2x. I would put that in your drawing if I were you. TR is y plus 4. QT, you're just a little cutie, aren't you? X plus 2. And TS is y. That's one of those T-shirts that I thought about buying. Is QT and a pi symbol for Pi Day for my daughter. Cutie pie. Be good. Never mind. I sidetrack. I digress. So if I look at these two things, and I'm talking about a parallelogram, and I'm talking about a diagonal and another diagonal, if I know it's a parallelogram, then the diagonals must bisect each other. They must cut each other right at the midpoint, and this piece here should be equal to that piece there. The 2x should be equal to the y plus 4, and the x plus 2 should be equal to the y. And this is where I think some of you might need a reminder. You have a variable with you have an equation with 2 variables. You have another equation with 2 variables. You can't solve it unless you use something you learned last year, which is called systems of equations. You have 3 ways you can solve it: by graphing, by the addition method, or the substitution method. It's up to you. You decide. For me, if I know what one of the variables is equal to, I'm going to use substitution. Since I know that y is equal to the x plus 2, I'm going to use that in the other equation. Y is the same thing as x plus 2, so I'm going to swap out, instead of y, I'm going to put x plus 2 in its place, and everything else is going to stay the same. That's going to come down, the plus 4 comes down, and the only difference is I change out the y to an x plus 2. And I solve it. You never just solve for one variable. You always solve for both variables, because we have to figure out what x is and what y is. And you could do this with addition or elimination, but you would need to move the 2 over to get the variables to line up, and then you would have to multiply one of these things by a negative to figure that out. I have one more example, and I have a theorem I need to read to you, which I think is pretty simple theorem. It doesn't have a name. It's called Theorem 44. If 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. This is a really cool thing. If I know that these two are congruent, then every other transversal is going to have to be congruent down the line. Not necessarily to the first one, but to each other. Way I could see this being used. Well, let's do a problem, and then I'm going to show you how I think this could be used. This is what the problems look like. In the figure, PQ is equal to QR is equal to RS. These 3 things are congruent, and these are parallel. And you have to figure out what ZU is. We got to figure out how long this is. Well, if these 3 are congruent to each other, then this has to be congruent to this, has to be congruent to this. So you would know how long ZU is. ZU is how long? Let me show you some interesting type of math that you can actually do this in real life if you wanted to. Let's say you see these lines and they're all parallel. I have 1, 2, 3, 4, 5 different lines, and they're all parallel to each other. Are all these distances the same distance?
We don't know.
Let's measure. What if I told you that these are all congruent to each other? Let's do it like that. Okay? And let's say, for instance, I have this rubber band, and I want this rubber band divided into 5 equal pieces. Instead of measuring, all I have to do is take my rubber band, go to the very start of here, put this down to the bottom where the 5th one is, if I could keep this straight and not without stretching anything, which is not going to be easy. And assuming I had a nice straight line, let's say a piece of string, if I cut here and here and here and here and here, then I would have 5 equal pieces. And I didn't even have to measure it to figure out where I would need to cut it. If I had something longer and I want to cut it into 4 pieces, let's take it to that point. 1, 2, 3, 4. Nice equal pieces. This has a lot of practical uses for anybody who's going to be working with fabric in their life and needs equal pieces, and or my guess is flooring, tile work. Somebody who's going to be making a lot of cuts with parallel lines. Just saying, real life math you could use to save yourself some time in the big scheme of things. I'm going to stop your notes right there.